Hi, everyone. I'm going to do the homework for 7 and 8 tonight. Course 8 was all of our rotational motion stuff. A little bit little bit of Newton's laws. So our first one, we have two masses, one connected by a string, and well, they're both connected by a string, but one that's rotating in circular motion and one that's hanging through that hole. The biggest thing on this is the one that's hanging through the hole won't go up or down. So if we look at our free body diagram of these two, we have that the one that's hanging, that they are calling mass 2, it has a tension upward due to that string, and it has a weight downward of m2g. And we'll assume that the acceleration is trying to be down. The one that's spinning around, if we look, has a normal force and a weight, but it's also trying to be pulled that way by a tension. And it also has an acceleration, but this is actually a rad. So if you remember that a rad is v squared over r, what we get is we get that m2a is m2g minus t, and a is 0. So this is 0 because mass 2 can't fall. So we know that the tension in the string is m2g. Now this one, in the direction along the rope, we don't actually care about the direction perpendicular or up and down. We only have the tension. So that tension becomes m2g. But a rad is v squared over r, is m2g. So if we want to find the velocity that m1 will have to rotate at to keep m2 from moving up or down, we solve this for v. So v squared is m2g, multiply both sides by r, divide both sides by m1, and then take the square root. And so our velocity is m2 over m1 times gr, 2 over m1 times gr. And they don't want you to actually solve it. They just want you to enter that as variables. All right. Now, if we go back to these and we remember that when a car goes over a hill, if we assume that it's trying to move in uniform circular motion around the hill. So we look at a free body diagram. It has to have a normal up because it's on the surface. It has to have mg down, but because it's moving in what we assume is the uniform circular motion, the acceleration is a rad. So what we get is ma rad. And I'm sorry, I drew that wrong because I'm being dumb. Spin along day is down. The radial or centripetal acceleration is going to pull it toward the circle. So this would be mg minus n. Okay. Now, we assume that this is mv squared over r is mg minus n. However, now we need to think about something. As the car goes over the hill, right before it leaves the hill, n is going to go to 0. So if this n goes to 0, we assume that there's no normal force on the car. Our m's cancel. And what we get is that v squared is gr, and take the square root. Okay. And so the speed, the maximum speed this can go before it leaves the surface is g times r. Now our r is 45 meters, g is 9.8, so v is 9.8 times 45, and that will give us what's shown here, 21 meters per second. I'm going to double check that with my calculator again to be sure. 9.8 times 45. Take that square root, and I get 21. So this is 21. But the key ideas here are that ARAD is down. It has a normal force in mg because there is no force along the path that it takes along the hill. But if it were to completely lose its normal force, what would happen is it would eventually take off the road. So we assume that the normal force has to go to 0, and we replace A with a radial or a centripetal, which is v squared over r. Not too bad. Okay. Now, in this one, we want to know the minimum angular velocity if we swing a bucket of water around in a circle, assuming that the distance from the handle to the bottom of the bucket is 35 centimeters. We got a couple of unit conversions to do, but imagine that your hand is grabbing this bucket and the bucket looks like this. Okay, and as you swing it in a circle at the bottom, it's going to look like this, and it swings around. And there's water inside, and you want to keep that water inside. What we're concerned with is at the top, and so our R is actually, I'll draw that in red. Our R is actually the distance from the handle to the bottom of the bucket. If we look at the water, it has a weight, mg. It has a normal force off the surface, so a normal force that's also down, and ARAD also pushes down. This is all at the top of the bucket. So you have a normal force, you have a weight, and ARAD is going to be downward. So I get that MARAD is N plus mg. And again, radial velocity is v squared over, or radial acceleration is v squared over r. Okay. At the minimum angular velocity, n goes away. So n is 0. So what we get is, again, what we got before. V squared is gr, or v is g over r. Now, we were told that our radius was 35 centimeters, or 0.35 meters. And so I can find this in meters per second. Square root of 9.8 times 0.35 is 1.85 rad per, or sorry, meters per second, actually 1.852. And I need to convert this into revolutions per minute, okay? So I need to figure out how many revolutions per minute this is. All right, so the period of one revolution is 2 pi r over v. This is in seconds, okay? Now, 2 pi r over v, this was 2 pi times 0.35 over 1.852. And this is the number of seconds in a period, or one revolution. So 2 times pi times 0.35 divided by 1.852 gives me 1.187 seconds, and maybe even keep the 4 seconds per revolution. Now, I want to know revolutions per minute. So the number of revolutions per minute. And that means that I need to take 60 seconds per minute and multiply that by my period, or divide that, sorry, by my period. My period is in seconds per revolution, and what I get is revolutions per minute. So 60 divided by 1.1874 gives me 50.53, or 50.5 revolutions per minute. for RPMs. Why do I have that so far off? So they have 9.8. Oh, why? Why? So this is G. Oh, shoot. I'm so sorry, you guys. I did something wrong, and that's okay. We can back up for a second. What I forgot is this, I didn't read the question very well. You have 65 centimeter long arms. So your arm, the total length of your arm, and then holding this bucket of water. So we'll redo this anyway. And then up to the bucket. And so what we get here is the following, okay? So as we swing this thing over our heads in uniform circular motion, again, V is G times R. Now, we need to start from our shoulder and get the total length, okay? So R is the length of our arm plus the length from the handle to the water. And that is the length of our arm, we're told is 65 centimeters. And the handle to the bucket was 0.35. And I don't know why I'm calling that centimeters, meters. If I add these together, I get 1.00 meters, or 1 meter. Okay. So my velocity is really 9.8 times 1, or square root of 9.8, which is 3.3 or 3.13 meters per second. Now, we want revolutions per minute. So again, the period is 2 pi r over v. Another thing that we could do is we could find omega, and remember that v is r omega. So omega is v over r, and this is how they did it. So that means that our period is 2 pi over omega. Now omega is 3.13 meters per second over 1 meter, and that gives us rads per second. So this just becomes 2 pi over 3.13. And that's our period in seconds. So 2 times pi divided by 3.13 is about 2.007 seconds. And again, if I take 60 seconds and divide it by 2.007, I get about 30 revolutions per minute. Okay. This is seconds per revolution, and this is seconds per minute, as I did before. Now, what they've done here is they actually found omega. However, they didn't quite find omega because omega is in radians per second. And what we found was that our omega was 3.13 rads per second. However, if we multiply that by 60 seconds, and then we divide that, so that will give us how many radians, and this will be the radians in 1 minute. Once we find that, if we then divide it by 2 pi rads per revolution, because as it goes around once, it pulls through 2 pi rad, we can find the number of revolution per minute. So that means 3.13 times 60 divided by 2 times pi, which is again about 30 RPMs. And so what they've got there is they have omega times, omega times over 2 pi times 60 seconds. And this was 1 over our period. So this is just 60 divided by our period, which is what I did. So yeah, it's just a little weird. It's Wiley being weird. All right. And now finally, we have a car that's just barely making a turn at 27 kilometers an hour. Let's put this in meters per second. Okay. We want to send this to meters per second. So 27 kilometers per hour. In 1 kilometer, there are 1,000 meters. And in 1 hour, there are 60 minutes times 60 seconds, or why do I keep 1 hour? There are 3,600 seconds. So 27 times 1,000 divided by 3,600. This is 7.5 meters per second. Now, what this is saying is the car's maximum cornering speed on a rainy day. So this is as fast as it can go on a dry day, or 7.5. But what happens when its coefficient of static friction is reduced by 50% because it's raining? So to go back and look at this, when we're on a flat road and we're taking a turn in our car. So as we're going along at constant speed, we assume uniform circular motion. We have this A radial to the inside. Now, our car has a normal force, and it has mg down, and it has static friction that's pushing it to the center. That's mu n, okay? So this is our A rad, or our A centripetal. M A rad is mu n, or M A rad, because mu is, or n is equal to mg. So our A rad is mu g. Cancel your m's. Or v squared over r is mu times g. Or v is mu g times r. Now what they're saying is when it rains, our speed gets reduced by a half. So what we get on this side is we would multiply this, or divide it by a half, which is the same as multiplying the whole thing by a half. So on this side, we're going to multiply it by a half as well. And what that's going to give us is square root of 0.5 is 0.77, 0.707. And our velocity was 7.5. So 0.707 times 7.5 is 5.3 meters per second. Now you could have actually gone through and found, mu. So what we could have done is v squared was mu gr, okay? We know that v was 7.5 meters per second on a sunny day. So mu is v squared over gr. I don't know what, they didn't tell us what r was, so never mind, we can't do that. All we can do is realize, like I said, that if v is equal to, gr, but we have to multiply 1/2 times mu because it's raining. Well, we have to do that to both sides of the equation. So we also have to multiply v by square root of 1/2. And this ends up being whatever it was, 5.3 meters per second. Put that back into kilometers per hour, I guess, or leave it as kilometers per hour, I guess. We originally had 27 kilometers per hour. multiply that by square root of 2 times 27. I'm sorry, square root of a half times 27 is 19 kilometers per hour. Anyway, all that said and done. Onward to, now we're going back to chapter 7. In chapter 7 was all friction, homework 6, and we have 7 problems here. Hopefully I won't be so scatterbrained. I don't know why I'm so scatterbrained right now, but so in this problem, we have a 1,000-kilogram car. It's being pushed, or it's pushing an out of gear truck. So it's pushing a truck that can roll. But the truck weighs 3,000 kilograms. The driver steps on the accelerator and the car pushes against the ground with a force of 6,500 newtons. And there is no rolling friction here. Okay. So what is the magnitude of the force of the car? So we're just going to assume that we have a truck that's out of a truck that's not, sorry, I don't know how to say this. The truck's not moving and it's in neutral. So the car is going to push with a force on the truck. And if we draw the car is going to push with a force on the truck. There is a normal force on the car due to the truck. On the truck, there is a normal force on the truck due to the car. Now, a different normal force, the normal force of the ground, but we don't really care about this. And the truck has a normal force, but we don't care about that either. But now what we're going to do is we're going to assume the acceleration is that way. So the car starts its engine and starts pushing the truck in that direction. Okay. Now, if we were to write these equations, m of the car, A, is F minus, and I'm just going to call this N. I'm going to call this N. They're the same normal force. M of the truck, A, is N. So I can see that this is MCA is the force minus M truck A. Add that over. And what I get is that MC plus MT times A is the force of the car. A is the force divided by the total mass. That was a very long way to do something simple. So if the car can push with a force of 6,500, our force is 6,500 newtons. The mass was 1,000 for the car and 3,000 for the truck, and 6,500 divided by 4,000 is 1.625 meters per second squared. Okay. Now, I know what that is, but that's not what they asked me for. They asked me for what is the magnitude of the force of the car on the truck. So what they're actually asking me for is what is the normal force of the car on the truck, but it's the same as the normal force on the truck. So this would be 3,000 times 1.625, and mass of the truck times A, which is about 4,900. Or if you did it over here, N would equal F minus MCA, which was 6,500 minus 1,000 times 1.625. And that again would be about 4,900 newtons. So as the car pushes this truck, it pushes it with a force of 6,500 newtons, but they want the normal force acting between the two. And because they're touching, treat them like they're surfaces that are in contact, they each get a normal force. It's a little weird problem. But as you see here, force of car on truck, force of truck on car, force of the car on the ground. the push force is here. And once you find A, you can then put it in and solve it. What is the magnitude that the force of the truck exerts on the car? Same thing. They are a third law pair. So the normal force on the truck due to the car and the normal force on the car due to the truck are equal and opposite. Now, I don't know why they don't just switch these around, but kind of weird to have the car pushing the truck. All right. In this next problem, we have two sleds, one's 100, one's 80, being pulled by a dog. And we're going to find the tension in these ropes. Now, there is a coefficient of friction of 0.08. So there's some coefficient of friction of 0.08, 100 and 100 kilograms and 80 kilograms. And when we look at this, we can treat this as two blocks. It's moving, so we only need to worry about kinetic friction. We have two sleds, and then they're hooked to the dog, but the dog's just going to pull. So this tension of the right, tension on the left, rope on the left, rope on the right. This is our 100 and this is our 80. And I'm just going to call this 1 and call this 2. So my free body diagram is N1, M1G. There's a tension, which I'm going to call the tension to the left. There's a force of friction, mu N1. For my second, I have N2, M2G. I have the tension of the rope on the right. I have the tension on the rope on the left. And I have, again, mu N2. I'm going to assume my acceleration is going that way. Now, the sled dog drags sleds A and B across the snow. Coefficient of friction at 0.08. I think we are supposed to assume that the I think we're supposed to assume, well, maybe we're not supposed to assume that yet. Yeah, we are. So I think we need to find the tension in the rope that the dog is pulling. We need to find how much this guy needs to pull. Assuming that the tension in rope 1 is 140 newtons. So how do we do this? Well, if we could look back, we have M1A is tension in the left minus mu N1, but N1 was M1G. And M2A, we assume, was tension on the right, minus tension on the left, minus mu N2, and N2 was M2G. M1 was 100 kilograms, M2 was 80 kilograms, mu was 0.08. So we need to figure out if rope 1, the one that we're calling T left, is 140 newtons. So if T left is 140 newtons, we want to find T right. Now, we are, I guess, going to assume, and let's see, I don't know if we're going to assume that they're moving at constant velocity. But if they are moving at constant velocity, A is 0. So I get 0 is T left cancels, and I get that T right is I get T right minus mu N1 minus mu N2, which means that TR is mu N1 plus N2, and move those over, which is mu times M1 plus M2 times G. Now, mu was 0.08. 100 plus 80 is 180, and 9.8. This becomes 0.08, 100 plus 80 times 9.8, and I get 141 newtons. Oh, well, I must have something, or they have something flipped. Why do they have? Oh, I think I'm being dumb. All right, so let's do this over again. Man, I am just on it tonight. M1A was T left minus mu N1, and M2A was T right minus T left minus mu N2. I guess I can't assume that they're moving a constant. Since I can't assume that, I know that T left is 140 newtons, we're told. So let's find A. M1A is TL minus mu, but N1 was M1G, which was 100 times 9.8. N2 is M2G, which is 80 times 9.8. So this is mu N1, and I want to solve it for A. So divide by M1. This becomes 140 minus 0.08 times 100 times 9.8 over 100. And so my acceleration is 140 minus 0.08 times 100 times 9.8 divided by 100. And I get my acceleration at 0.616 meters per second squared. Now going back to here, what I'm going to do is I know my acceleration is 0.616 meters per second squared, and I want to find T right. I want to find the tension in rope 2. So the tension on the right, add these over, is M2A plus tension on the left plus mu N2, which was M2G. So this is 80 times 0.616 plus 140 plus 0.08 plus 80 times 9.8. When you do all that, 80 times 0.616 plus 140 plus 0.08 times 9.8 times 80, I get 252 newtons. I think they round it to 250. They did. All right. Now, yeah. That's all. I'm not sure where they got the 1.8 times T for this, but I'm sure that if you looked at rope 2 has to pull both masses. So it's got whatever the tension is here, plus, so 1 times that, plus an additional 0.8 times that tension. And I think they just cut it and said, oh, well, the tension in this guy is 140. And so the tension in here, because it has to almost double. If this was also 100, this tension would be double that. But because it's not quite double, it's only 0.8. The tension in rope 2 is 1.8 times the tension in rope 1. That actually works, but I would rather you knew how to get it the long way. And again, I assumed at the beginning that it was constant velocity, but I didn't need to assume that. I couldn't assume that actually. So I had to do it the long way. All right. Now, this one is 2 blocks are attached at opposite ends of a massless rope over a massive friction poly. One of the blocks with a mass of 2 kilograms accelerates downward at 3/4 G. What this is the so-called Atwood machine. And I'm going to assume this Atwood machine is going to move down that way. And so 1's going to fall and 2 is going to go up. If I look at my free body diagrams, tension in the rope, M1G, A is down, tension in the rope, M2G, A is up, and I get M1A is M1G minus T, M2A is T minus M1G, the T's cancel, and I get M1 plus M2A is plus M2 is, and I don't need to do this. You'll see what I actually need to do something different. But that is the equation of an Atwood machine. If M1 is bigger than M2, then the acceleration will be positive in the direction we chose. If M2 were bigger than M1, the acceleration would be negative. We want to find mass 2 though. So let's actually solve this for mass 1 versus mass 2. I have M1A plus M2A is equal to M1G minus M2G. Put everything with mass 1 on this side and everything with mass 2 on this side. So I get M1A plus or A minus G. Move that over and you have to subtract it. And over here I get M2. So I get, actually, let's do this the opposite way. Let's move all our M1s over to the other side. So on this side, I get M2A, move that over, and I get plus G is equal to M1G minus A. All right. That's just combining like terms. That means that M2 is related to M1 by the following ratio: G minus A over A plus G or G plus A. Now, we're told that one of the masses, let's call it mass 1, is 2 kilograms. And we're told that mass 1's acceleration is 3/4 G, positive 3/4 G. So 3/4 times 9.8. And we want to find mass 2. So you're going to assume that G is 9.8 and A is 3/4 G. Well, all the G's will cancel. So I get M2 is M1, which was 2 kilograms, times G minus 3/4 G over 3/4 G plus G. You can cancel G out of this by turning all the G's into 1s. So what I get is 1 minus 3/4, 1 plus 3/4. This is the same thing as 2 times 0.25 over 1.75. To do that, 0.25 divided by 1.75 times 2 is, this answer is 0.286 kilograms or 290 grams. I don't know which way they want it. So 0.29 kilograms, 290 grams. All right. So it's an Atwood machine, but you have to do a little bit more work than normal to solve for M2, given that M1 is 2 and A is 3/4 times 9.81. All righty. Now, you are a 75 kilogram person with a crossbow and ice skates on smooth ice, fires a bolt with mass 530 grams, horizontally to the right. When released, the bolt reaches a speed of 110 meters per second. What is the force in 0.25 seconds? What is the force of the bolt on the crossbow that the crossbow man is holding? All right. First of all, remember that acceleration is the change of velocity over time, or v final minus v initial over t final minus t initial, but we'll just call that t. It went from 0 to 110 meters per second. So this is 110 minus 0 over 0.25 seconds. So the acceleration on that bolt was 110 times 0.25, with 27 0.5 meters per second squared. Now, as you shoot your crossbow on your ice skates, whatever force acts on the arrow also acts, or the bolt, I should say, also acts on the crossbowman. Well, the force on the arrow is its mass times its acceleration. And it had 530 grams, or 0.530 times 27.5. The force on the arrow was 0.530 times 27.5, or 14.6 newtons. All right. What is the force on the bolt on the crossbowman? Y. Did I do something weird there? Did I calculate something off? What should have? So this is MA. Oh, I'm just being dumb. Okay. I'm just being dumb. So when released, or actually technically I think they're being done. But they're assuming that they accelerate at the same rate. Okay. So the force on So the force on the man is actually, they have the same acceleration. So as the bolt flies away, the man flies away with the same acceleration. The force on the man is MA, and that means he had 75 kilograms and his acceleration was 27.5 meters per second squared. So this force is 75 times 27.5. Why? What are they? I must have an error somewhere in here, because yeah, this doesn't seem to be 110 divided by 0.25 is 440. Oh, maybe I'm just so sorry, you guys. Yeah, I was right the first time. I just did something wrong. Oh, what a day. All right. I can't use my calculator correctly today. So yeah, I wrote this wrong. I'm just done. What I did wrong here was this is not 27.5. I don't know what I got there. 110 divided by 0.25 is 440 meters per second squared. So this force is 440 meters per second squared. And the force on the arrow is 0.530 times 440, or 233.2 newtons. Now, as I said before, and I started confusing myself, because don't ever look at answers and then try to justify your answers based on what, like you know something's wrong and you're trying to figure it out. You're always wrong. So the force acting on the bolt and the force acting on the man, so this is our little arrow shooting off the crossbow, and this is our man, they have to have equal and opposite forces by Newton's third law. However, the mass of the man is 75 kilograms. The mass of the arrow was 0.53 grams or 0.53 kilograms. And the acceleration was the change of velocity over t, which was 110 meters per second divided by 0.25 seconds, or 440 meters per second squared. So the force on the arrow, or bolt, it's called a crossbow bolt, is the mass of the arrow times the acceleration, or 440 times 0.530, which ends up being 233 newtons, 0.2 newtons. That'll be the same force on the man. What is the acceleration of the man? A is the force over the man's mass, which is 233.2 over 75. This is 3.109 meters per second squared. And by the way, that force is negative. His final velocity as he recoils, so again, if its acceleration is negative 3.109 meters per second squared, acceleration is v final minus v initial over t. We assume this goes away, and v final is a t, or negative 3.109 times 0.25 seconds. So times 0.25. That is negative 0.777 meters per second, or 0.78, but it's negative. And this force is negative. So just so you know. Yeah, I'm sorry, I messed that all up. Being dumb. Okay, so these last three are not too bad. Frictionless surface. We have two masses, and we're going to call them big M and little m. Big M and little m. Now the free body diagram for big M, no friction. So normal force, big mg, and a tension. And I'm going to say that A goes this way and Y goes up. And then for little m, I have a tension and I have little mg. And I'm going to assume that the acceleration goes down for little m. So I get big M A is t, and little m A is little mg minus t. Adding those two things together, I get big M plus little m times A, t's cancel, is little mg. They want to know what is the tension in the string. So if I use this equation, I get little m A, I do that. So let's solve this one for t. T is, move it over, and then move little mg minus little ma. Okay. And so if I plug that in here, I get big MA is T, but A is T over big M, and T is little mg minus little ma. So this is little m times g minus a, or little m, do I want to do it this way? This is kind of a pain in the butt. So let's actually do this. So T is mg minus m times T over big M. Move that over and I get the T plus T times little m over big M is equal to mg, or T times 1 plus little m over big M is little mg, or T is equal to little mg over 1 plus little m over big M. If I multiply top and bottom by big M, what happens is that goes away and this bottom part becomes little m plus big M. So multiply through both sides by big M, and what do you see happens? This becomes big M, this cancels. So we get this. Little m g big M over little m plus big M. Little m big M g over m plus little m. Okay. Now, 4 kilogram block, frictionless surface, blah, 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 hanging. For what value of the hanging mass does the block accelerate at 1.8? Okay. So what this is saying is if we go back to this, it's saying that this one is 4 kilograms, and we want to know what mass this is if A is equal to 1.8 meters per second squared. So we want to find little m if big M is 4 kilograms and A is 1.8. So using what they found, if we back up a minute, sorry, big M was 4 kilograms, I think. That's how we do it, yeah. And A was 1.8 meters per second squared, and we found that the tension was little m big mg over m plus big M. But that's not really the one I want to use because I'm trying to find little m. So the tension is also, if I just get rid of all this, if I go back and look, the tension was big MA. So big MA, the tension is 4 times 1.8, which is 4 times 0.8 is 7.2 newtons. And little m A was equal to mg minus t. Okay. So that means if I move g over, m A minus g is equal to negative t, just subtract mg. Or little m is negative t over A minus g, divide both sides by A minus g. If I multiply by both by -1, I get t over g minus A. So I get 7.2 over 9.8 minus 1.8, which is 7.2 divided by 8, or 7.2, 0.9. So 0.9 kilograms. So just go back and use these equations, solve for t, plug it in here, and solve for little m. 0.9 kilograms, not too bad. All right, now we have these three, and we have friction between this guy. Now we know that this block has to drop because it's more massive than this block. So 1, 2, 3, and the coefficient is 0.34. All right, so I have 3 masses. 1, 2, and 3. They are going to go this way. This one's going to fall. This one's going to go to the right. This one's going to go up. My free body diagrams look like this. T, I'm going to call this rope TL and this rope TR. So M1G and A will be up. For 2, I have N, M2G, and this is M2. I have TR, and I have T. Sorry, I should have called this T left. And I have friction, which is mu N2. Remember that mu was given as 0.34. The masses are 1 kilogram, 2 kilograms, 3 kilograms. And A will go that way. And then finally, I have M3G I have T right, and I have A down. Now I know for mass 2, AY is 0, so N2 minus M2G, or the normal force on the middle one is M2G. If I want to write these three Newton's equations, I get M1A is T to the left minus M1G. M2A is T right minus T left minus mu M2G. And M3A is M3G minus T to the right. All that stuff's going to cancel, and what I get is I get that M1 plus M2 plus M3A is M3G minus M1G minus mu M2G. Now that I have that, what is the acceleration of the 2 kilogram block? Well, it's the same for all of them. So it ended up being M1 plus M2 plus M3A was M3G minus M1G minus mu M2G. Now, if I move this over, they all have the same acceleration. This is M1 plus M2 plus M3. And remember, 1, 2, and 3 had 1 kilogram, 2 kilograms, 3 kilograms, and mu was 0.34, I believe. 0.34. So I get A is 3 times 9.8 minus 1 times 9.8 minus 0.34 times 2 times 9.8 over 1 plus 2 plus 3. So I get 2.156 or 2.16 meters per second squared. Or 2.2. They're rounding it up to 2.2. So just make sure you know how to write the free body diagram for a hanging mass or a mass on a horizontal surface. You do have friction. You had to know which way this thing was going to go. But if you look at this problem, 3 is going to fall, 1's going to rise, because 3 is more massive than 1. So you know that the friction on 2 has to point back to the left because it's going to the right. Make sure that you call these tensions tension to the left, these tensions are tension to the right, or tension 1 are the 2 on the left, tension 2 is the 2 on the right, whatever you want to call it. But those ropes have different tensions. And from there, to the left is what I called the rope between 1 and 2. To the right is what I called the rope between 2 and 3. Those cancel when you add all these equations together. And it's not too bad of a problem, actually. All right. And they are using 9.81 in there, but our final problem. So now we have static friction and kinetic friction in this problem. But we can see that the book is connected by a string to a cup. So this may not look like it, but this is simply mass on an incline connected over a rope. So this is my book and this is my cup. I have a normal. Remember, you're going to turn your book on its side and it's going to have a normal. It's going to have mg sine and it's going to have mg cos. All right. Mg cosine. This is for the book. Mg sine. Now the cup looks like the following. It has a tension upward. It has mass of the cup times g. So I need to make sure I also have a tension here. And I'm going to assume that this thing's going to go up the incline, A. So if I look at this problem, the book's sliding up the incline. I know my angle's 20 degrees. But now I need to know, assuming that it's sliding, so assuming that it's heading up the incline, all right, I need to find the acceleration first. I need to find the acceleration. It has a coefficient of static friction of, mu k is 0.20. So since the book is sliding upward, my friction is mu n. But here, m book ay is 0, is nb minus mbg cos theta. So the normal force on the book is mbg cos. Now looking at my two equations, m of the cup A is going to be upward. It's mcg minus, T minus mcg. Looking at my book, okay, there's no force pulling it upward. So MBA is negative T, negative MBG sine, negative mu MBG cos. This is the force of friction that was mu n. Okay, if I add those two things together, I get mass of the cup plus mass of the book, A. The T's cancel. This is T and this is minus T. And I get minus mcg, mass of the cup times T, minus the mass of the book times G times sine of the angle, minus the force of friction. And what I get here, if I divide both sides by the total mass, I get A, mass of the cup plus mass of the book. Now my mass of my cup and my mass of my book are, mass of my cup was 250 grams, so 0.250. Mass of my book is 1.3. These are both in kilograms. My angle is 20 degrees. It's on the picture. And mu k, not mu s. I don't need mu s in this problem. Mu s is the static friction, but it's already assumed to be moving. So mu k was 0.20, I think, right? All right. So having all those, I get that A is negative 0.25 times 9.8 minus 1.3 times 9.8 times sine of 20 minus 0.20 times 1.3 times 9.8 times cos of 20, all divided by, this is the first term, 0.25 plus 1.3. All right, so my acceleration is 0.25 times 9.8 plus 1.3 times 9.8 sine of 20 plus 0.20 times 1.3 times 9.8 times cosine of 20, and then divide that whole thing by 1.55. And my acceleration is 5.937. A is 5.937 down the incline. All right. Now, how far does the book slide? It's given an initial speed of 2.5 meters per second. The book, okay, is going up the incline with some initial speed. The acceleration is along the incline, so you need to make sure and turn this. This is my x initial, where it starts. This is some x final, where it ends, and that's what I want. I know that it has an initial velocity of whatever it was, 2.5 meters per second. When it stops sliding, B final will be 0, and A is that way, and it's 5.937. So x initial X final, V initial, V final, A and T. A is negative 5.937 meters per second squared. X initial is 0. X final is what I want. V initial was 2.5 meters per second. V final is 0 because it comes to rest. I don't know T. X final minus X initial is V naught T. Sorry. Yeah, V naught T plus AT squared over 2, but that has time in it. V final is V initial plus AT, has time in it. V final squared minus V initial squared is 2A, X final minus X initial. This is the one I want. I want to find X final. V final is 0. X initial is 0. So I get negative V naught squared is 2A X final. Divide both sides by 2A, and this goes away. And what I get is negative 2.5 squared over 2 times negative 5.937. So 2.5 times 2.5 divided by is 0.526 meters or 53 centimeters. 0.53 meters, 53 centimeters. At its high point, does the block stick? Okay. So first of all, I think we probably all got this down and this down. But now, when it comes to rest at the top, okay, so when it stops momentarily, it's going to try to slide backwards. If we look at this, okay, what we have is we go back to actually this. Coming back to here, let's get rid of this for a second. Okay, this is still true. But now what we don't know is, let's assume instead that it's going to try to go down. So it's going to try to go back down. The net force on the system, or on the book really, is M book A is MBG sine theta minus or plus T, and MCA is MCG minus T. So adding those together, what I see is without friction, I have MB plus MC A. MBG sine theta is MBG sine theta plus MCG. And all this is saying that when this thing stops momentarily, and it's still connected to the coffee cup, so this is my book and this is my cup, gravity's trying to make it slide down with a force MBG sine theta. And gravity's pulling the cup down. And because they're connected, those two forces are actually the two external forces that are trying to pull this guy down. However, as it's trying to be pulled down, there's going to be momentarily static friction, mu s n on the book. That static friction is going to try to counter these two forces because A is 0 and this is minus mu static n of the book. So whichever one wins, remember that n of the book was MBG cosine theta. So whichever one of these wins, we'll learn, and I should put a question mark here. If static friction is greater, if this side is greater than this side, static friction wins. And the book doesn't go anywhere. If they're equal, it still shouldn't go anywhere. That's kind of debatable, but we'll assume that if it's equal or less, if this side is equal or less, doesn't move. Okay, so let's figure out what these are. Mu S was 0.5, so this is 0.5. This was 1.3, this is 9.8, and this is cos of 20. This is 1.3, 9.8, sine of 20, and I forget what it was, 0.25? 0.25 times 9.8. All right, so you could eliminate M and G. Well, you could eliminate G from both sides, but I wouldn't bother. 0.5 times 1.3 times 9.8 cosine of 20 is 5.985 newtons. That is the force of static friction. And if the other forces are not equal or greater, the book's not going to slide anymore. Static friction will hold it on the incline. So this side is 1.3 times 9.8 times sine of 20 plus 0.25 times 9.8, 6.87. So unfortunately, that means it's going to slide back down. Okay. Does the book slide back down the hill? Yes, because the net force, if there were no static friction, is greater than the amount of static friction on the book alone. Hopefully that makes sense to you. Static friction is a pain. It won't be on the exam. I know I'm super tired today, you guys. I was a little off as I was trying to go through this. There is a video tutor solution to this. If you don't like my solution, please watch it. I hope all of you have a good weekend. Please make sure you sleep Monday night. The best thing you can do before an exam is get a good night's sleep. And I will see you all Tuesday. So good luck. See you soon.